Right. As you can see this, the total pressure of the system should be in between the saturated vapor pressure of two liquids, right? So when you get ideal solution, the total pressure should be in between the saturated vapor pressure of two pure liquids, right? Total pressure greater than one and less than the other. It should be always in between these two saturated uh, vapor pressure of pure liquids. Let's have that one also. Write this. Red line variation of vapor pressure of A, blue line variation of vapor pressure of B, and black line is variation of vapor pressure of total vapor pressure of the system, and that's in between saturated vapor pressure of pure liquid. That's what you should understand. Okay. Then here there is one more point. I can extend this graph one more step, right? So, but before I go to that one, I take a simple question and then discuss it. Yes. Let's have a question and then go to that one. Okay, let's write this simple question. Write simple question like this. AB ideal solution contains AB ideal solution contains AB ideal solution contains AB ideal solution contains 0.2 mole fraction of A, 0.2 of XA, mole fraction of A, and 0.8 mole fraction of B, 0.8 of XB. Saturated vapor pressure of pure A and B are saturated vapor pressures of pure A and B are pure A and B are pure A and B are it's given 200 mercury millimeter and 300 mercury millimeter respectively. 200 and 300 mercury millimeter respectively. Okay. Question is this. Calculate the mole fraction of A and B in vapor phase. Calculate the mole fraction of A. That means in vapor phase. That means X dash A. Calculate the mole fraction of A and B in the vapor phase. So you have to calculate X dash A and X dash B. That's what you asked to calculate. Okay, then we discussed how to do this type of calculation last week. Do it quickly. I'll give you about 3-4 minutes for that. All of you should do that one. Last week we did this type of applications, equations easily. What you are given, you have the system AB two substance and mole fraction of A directly given 0.2, mole fraction of B XP directly given 0.8, P naught A also given it's 200 and 300. Your question is to find out mole fraction of A in vapor phase and mole fraction of B in vapor phase. We know to get the mole fraction of A in vapor phase, we have to apply Dalton's law of partial pressure. For that, we need the vapor pressure of A and vapor pressure of B. To get the vapor pressure of A, you can then apply what? You can apply Raoult's law. If I apply Raoult's law to A, we can apply it like this. It's PA equals P naught A XA. That's the equation. P naught A I gave you 200 and XA I gave you 0.2 means 2 divided by 10. It's in mercury millimeter. So these two cancelled out. It's what? 40? 40? Yeah, 40 mercury millimeter. That's P. Then to B we can apply Raoult's law. It's then PB equals P naught B into xp. So what is P naught B value? P naught B value I gave you 300. 300. Then xp value is 8 over 10. So what is it? It's something like 10, 30, 240. Yeah. It's then 240. 240 mercury millimeter. Oh, that's what we get. Then, yeah, we have PA, PB. Then you can have the total pressure. PT equals PA plus PB. Dalton's law of partial pressure. 40 plus 240. It's 280 mercury millimeter. You see, it's a very, very simple thing. Total pressure 280 mercury millimeter. But now I need the mole fraction of A and B in the vapor phase. So how to find out? Now we can apply, since the mole fraction of vapor phase, you can apply Dalton's law of partial pressure, Dalton's law of partial pressure to A. Dalton's law of partial pressure, that's equal PA equals what? X dash A into PT. Everything should be for vapor phase, Dalton's law of partial pressure. Then X dash A equals PA. PA, it's 40, that's divided by 280. It's something like 0, 0 cancel, 4, this is 2 and actually 1 over 7. X dash A, 1 over 7. 1 over 7 is what? 0 0.143. 0 0.143. Then X dash B will be 1 minus X dash A. 1 minus 0 0.143. It will be 7, 5 and 9, 8. 0 0.857. 143, 857. These are the mole fraction of these components in the liquid vapor phase. These are the mole fractions of A and B in the vapor phase. Now, okay, I think you don't have a problem with the calculation part. Easy. Now I want to represent this mole fraction again in the diagram here. Again in the diagram. Now look at this. I go back to that vapor pressure composition diagram. Okay. Then what's the mole fraction of A I got in the liquid phase? In the liquid phase, 0.2. XA 0.2 mean it's somewhere here. This is where you get 0.2. 0.2. Then what is XB? XB is 0.8. XB is 0.8, right? For this liquid mixture, I can find out the total vapor pressure here. This line gives the total vapor pressure, you know. For this composition, total vapor pressure is what? Total vapor pressure is 280. P naught A, you know, P naught A, I got P naught A 200. This is P naught A, this is 200 mercury millimeter. P naught B, I got 300. So P naught B here, it's 300 mercury millimeter, not ATM now. This is not ATM. It's now mercury millimeter unit. He also mercury millimeter. But the total vapor pressure of this mixture, of this liquid mixture is 280. So where is 280? It's above 200, but below 300. So 280 is somewhere here, okay? Close to 300. So then look at this one. I can get the total vapor pressure for this liquid mixture as then this point. I move up to this line, this line. So this pressure will be then what? This pressure will be the total vapor pressure, that is 280 mercury millimeter. 280 mercury millimeter. That's the total vapor pressure of this liquid mixture. You understood it? Then I'm going to represent now mole fraction of A and B, composition of A and B in the vapor phase. In the vapor phase, at this total pressure 280. At this total pressure, I'm going to represent mole fraction of A and B in the vapor phase. Mole fraction of A and B in the vapor phase, you know, X dash A, we got 0.143, X dash A is 0.143, X dash B I got 857, 0.857. So how do we represent that one in the same graph, same diagram? Now look at this, 0.143. Where is 0.143? If this is 0.2, 0.143 should be before 0.2. Let's take this point. This is 1, then this is 0.1. 143. Let's take this point. That's 0.143. I take it like this. This point is 0.143, right? Just below that, it should be 0.857 because addition should be always 1. Then 0.143, look at this. 0.143 is the mole fraction of A in vapor phase. In vapor phase, when the total vapor pressure is 280. Therefore, that point is this one. That point is this one. So what's the meaning of this? This line, this dark line, this one, this line represent vapor pressure of the liquid mixture, vapor pressure of the liquid mixture, right? But then I can use the same graph to represent composition of components in vapor phase at the given total vapor pressure. So that line should be given, that line, that composition should be given using this type of line. Understand? So when you draw a line like this, that line should represent composition of components in the vapor phase at the given total vapor pressure. At the given total vapor pressure. Then here we did some calculation and I prove it. That point should be definitely below this line. Below this line, but it's not straight line. It has curved nature like this. It has a small curved nature like this. So therefore, you should understand in vapor pressure composition diagram. I erase this part now. Okay, I erase this part also now. Now you understood. By calculation, we proved that one, right? By calculation, we proved that one. If you get this type of vapor pressure composition diagram, remember straight line. This is straight line represent what? Vapor pressure of liquid mixture. Vapor pressure of liquid mixture. But if you draw a line below this like this, what does that represent? That line represent composition of components in vapor phase at the given total pressure. At the given total vapor pressure. Right. In that case now, look at this. Above this line, what do you find? Vapor phase or liquid phase? Above this line. This line represent vapor pressure of the system for a given liquid mixture. This line actually gives the composition of liquid, right? Above this line mean high pressure side, high pressure side, you see. If it is high pressure, where do you find that particle? That particle is found most probably in vapor or the liquid. If you maintain high pressure, where do you find that particle? Can I have 2-3 answers? If you find high pressure, where do you find normally particle? In a liquid phase or vapor phase? Yes. If the particles are under very high pressure, you know, high pressure mean small volume mean interparticle distance decreases. Particles get close to each other mean strong attraction, nicely packed. Yes, it should be in the liquid phase. Most probably it's in liquid phase. High pressure mean liquid phase. The previous diagram was not clear, so that's why I'm going to draw it again. This is composition. That composition then can be vapor phase composition or gas phase composition. It varies like this, 0, 1 and 1, 0, like this. Xa equals 1, Xa equals 1, it's P naught A. You get, if I use the previous one, I got P naught A smaller than P naught B. Then I got, I take P naught A somewhere here. This is P naught A. Xb equals 1, that is where we got P naught B. P naught B, greater than P naught A. Then there is a straight line here in the graph. There is a straight line here, like this. It's also straight line here. What is that straight line represent? That line represent vapor pressure of total vapor pressure of a liquid mixture. Therefore, when I put a certain pressure and take here and get the composition, what is that composition? That composition should be liquid phase composition. Certain pressure like this and come up to this line and come back to this. So what is that? It's the liquid phase composition. Liquid phase composition. This line gives liquid phase composition. Okay. Or total vapor pressure of certain liquid phase. Right? But sometimes we want to represent the mole fraction or composition of components in the vapor phase also at the given pressure. That is given by this line. Not the top line, but the below line. By calculation, I proved that one. So this is vapor. This is liquid. So remember then, above this line, what we have, liquid phase. Above that line, what we have, liquid phase. High pressure, liquid. High pressure is liquid. So this is vapor pressure. This is also vapor pressure. This is, let's say, in ATM. This is also in ATM. Correct. Then this line gives the vapor pressure of a liquid composition, liquid mixture, or you can say this line gives the composition of liquid phase. Above this line, there should be a liquid, but this below line then represent composition of vapor phase. That means this below line, we have low pressure. Here, low pressure side. Low pressure mean pressure low mean the volume is large. Volume is large mean the particles are well separated. Interparticle distance is large. That means very small attraction, weak attraction. It should be most probably a vapor. That particle should be found in vapor. This line gives composition of vapor. Then in between these two lines, you have the equilibrium. The particle is in equilibrium between vapor and liquid. So here we have liquid vapor equilibrium. Can you see that? It's liquid vapor equilibrium. Between two lines, we have liquid vapor equilibrium. Remember that one. Right. I hope you understood now the graph, complete graph. Ne? This is actually, we can say, vapor pressure composition phase diagram. Without this, just vapor pressure composition diagram, this can be vapor pressure composition phase diagram. All the phases available here. Without this line, actually, it's just the liquid phase. Composition of the liquid phase only. Below line mean the composition of vapor phase. Then all the phases available. That's a complete diagram. This line represents what? Below line. It's the composition of components in vapor phase. Vapor phase. What does this line represent? This line represent composition of components in liquid phase. Components in liquid phase. Okay, that's the complete diagram we have. Okay, start new point. You did that calculation. Eh? Below that, we write down. Shall we do some past paper question here based on this one? Do you have that confidence? So, yeah, 2019 paper has application of this. 2019 paper has application of this one. Shall we try that? It's okay. You can't get the answers, right? Because just after the theory, I go to past paper question. Then you may ask, what the hell then are you? You may then wonder why then I'm giving this, because I want to show you how the question is given in exam. Okay, let's try this. This is A-level 2019 paper, right? This is the part given from heterogeneous phase equilibrium. Okay. Then this is half of complete essay. I can show you the complete essay. Can you see that? This is complete essay. As you can see, then first part is given, but first part is given from KD. KD, calculate KD plus, no, not KD, ionic equilibrium. Ionic equilibrium given. Yeah, ionic equilibrium. It's about acid, weak acid, and titration. That part is given. pH curve, it's not difficult, right? Basic question is given. It's a titration between monoacidic, weak base, and acid HCl. So we have done this type of pH curves, calculation, everything. Part A. Sorry. If you need, you have to select it. Then second part is given heterogeneous phase equilibrium. Okay, then if I magnify this so that you can see it easily. This is the second part of this heterogeneous phase equilibrium. Right. It's okay. You can't get it. Then you see out of 150 marks, 75 marks given. 75 marks given. I'll give you about 7-8 minutes. Fast. Do it. Right. Let's see how to answer this question. Two experiments given. Both of these two experiments are at same temperature. Temperature is constant given. If the temperature is constant, remember P naught values are also constant. Two components given C and D, then P naught C in both experiment, same value because same temperature is there. D component is there, then P naught D is same in both experiment because temperature is constant. That's the first thing you should understand. Saturated vapor pressure of POC and D should be constant in both experiment. Why? Temperature is constant. That's the first thing we need to understand. If I go to experiment 1, what's the information given in experiment 1? Experiment 1, information given like this. CD introduced to evacuated rigid container and allowed to reach equilibrium. This is the system. You have C and D. Now we have equilibrium. The mole fraction of C and D in liquid phase given 0.3, 0.7. This is 0.3. This is 0.7. Those are mole fractions at liquid phase. It's given L1, the composition. Total vapor pressure of this system given 2.7, 10 to the power of 4. Total pressure given 2.7 into 10 to the power of 4 Pascal. That's PT. Not PA, not PB, but PT, total pressure. Better to identify these with the correct symbols, right? That's experiment 1. Then experiment 2 given. Experiment 2, what is that information? Again, we have C and D in the closed vessel, right? But now the compositions are quite different. Experiment was conducted using different amount of C and D. When equilibrium establishes for right. Then 0.6, X is 0.6 mole fraction. Then this should be 0.4. That those are mole fraction of liquid phase, but it's given L2, second liquid composition, and the total pressure in this system given 2.4 10 to the power of 4. Here PT given 2.4 10 to the power of 4 Pascal. 2.4 10 to the power of 4 Pascal. Right. Let's go to the questions like this. First one, give the relationship between PC, P naught C. You know, PC equals P naught C into XC. What is XC? XC is the mole fraction of liquid phase. XC is the mole fraction of liquid phase. Write the name of the law. What is it? Raoult's law. Law is Raoult's law, easy. Second part now. Calculate the saturated vapor pressure of C and D. How to calculate saturated vapor pressure of C and D? Since total pressure given, I can write the expression for the total pressure. So what is total pressure? Total pressure will be pressure exerted by C, that means PC, plus pressure exerted by D, that is PD. You can write it like this. PC plus PD equals PT. But what is PC now? PC can be expressed in terms of Raoult's law. You see, PC equals P naught C into XC. P naught C, we don't know that one. That's what you asked to find out. P naught C is the question actually. Saturated vapor pressure of POC, P naught C, we don't know. Into XC, what is XC? It's the mole fraction of C in the liquid phase. Do we know that? Yes. C in liquid phase in the first experiment, it's 0.3. Then P naught C into 0.3 plus, then PD. PD is P naught D into XC. P naught D, we don't know. That's what you have to find out. But XD, we know it's 0.7. That's equal PT. I'm talking about the first system, 2.7 10 to the power of 4 Pascal. I can rearrange it like that. This is something like 3 over 10, then 3 P naught C plus 7 P naught D equals 10 here. It's 2.7 10 to the power of 5 Pascal. Like this. This is first equation. Did you get this idea? 3 can be written like 3 over 10, 7 over 10. Then we take 10 to the other side. It's 10 to the power of 5 now. That's the equation. Then I take another equation like this, but using the experiment 2. This is according to experiment 1. Experiment 1. If you get experiment 2 data, that is again PC. PC is P naught C into XC. What about P naught C now? P naught C is same as this value because temperature constant. That's what I told you. But now the mole fraction of C in liquid phase 0.6 plus this will be point D into 0.4. That's equal to total pressure 2.4 10 to the power of 4 Pascal. 2.4 10 to the power of 4 Pascal. This can be something like 6 over 10, then 6 P naught C plus 4 P naught B, P naught D. That's equal, then 10 come to this, it becomes 2.4 10 to the power of 5 Pascal. This is second equation. Now within you have two unknown factors, parameters, then two equations, you can simplify them and find it out. Okay, how can we do that? 3 and 6, better to multiply this by 2. First one multiply by 2 and then subtract second one from this. This into 2 means 6P naught C, 6P naught C cancel out. This into 2 means 14P naught D minus 4P naught D equals this by 2, 5.4. This is 5.4 into 10 to the power of 5 Pascal minus 2.4 into 10 to the power of 5 Pascal. That's how we get it. 14 minus 4, it's 10P naught D. 10P naught D equals 5.4 minus 2.4, it's 3, 10 to the power of 5 Pascal. Then 10 cancelled out. 10 cancel with this, this is 4. Then P naught D, 3 10 to the power of 4 Pascal. That's P naught D. Then substitute P naught D to one of this and find out P naught C. That's easy. Can you see that part I wrote? Yes, you can see it. This is actually P naught D. That's Pascal, right? Okay, this is Pascal. P naught D, 3 × 10⁴. Okay, then you can substitute it to one of this first or second and find it out. Other one, that is P naught C. I get it like this. By first, let's say by first is okay. D we got 7. I think second one is good. By second, we can say 6P naught C. 6P naught C plus what is it? 4 × P naught D. 4 × P naught D, 3 × 10⁴ Pascal is equal to 2.4 × 10⁵. 2.4 10⁵ Pascal. 6P naught C now equals 2.4 minus, what is this? 2.4 10⁵. I write it like 24 10⁴. Then 24 minus 4 × 2, it's 12. 4 × 2, it's 4 × 3, it's 12. 10⁻⁴ Pascal. Then 6 P naught C equals now 24 minus 12, it's 12. 12 divided by 6, 10⁴ Pascal. It's actually 2 10⁴ Pascal. Can you see it? Yes, 2 10⁴ Pascal. This is 3 10⁴ Pascal. Those are the saturated vapor pressures of PO C and D. P naught C, 2 10⁴. P naught D, 3 10⁴. Those are the answers for second part. That's the big calculation we have in this question. Right. I hope you don't have a problem with that calculation. Just I apply Raoult's law and Dalton's law of partial pressure. What is next question? Calculate the mole fraction of CD in the vapor phase. Experiment 1. Calculate the mole fraction of CD in vapor phase of experiment 2. Now we have to find out the mole fraction of C and D in the vapor phase. Let's say X dash C. Mole fraction of C in the vapor phase, I take X dash C. Mole fraction of D in vapor phase, I take X dash D. You have to find out these things in the first and second system. Okay, then yes, I have to erase this one. Shall I erase this? Did you complete this? I need a mole fraction of C and D in the vapor phase. Remember, when you asked to calculate mole fraction in the vapor phase, we apply Dalton's law of partial pressure for these things. Then to C, we apply Dalton's law of partial pressure. In that case, it will be PC equals XC dash into PT. If you apply Dalton's law of partial pressure, everything should be for vapor phase. Then XC dash will be PC over PT. Do we know PC? PC. We did not calculate PC. Ne? We got P naught C and mole fraction. Okay. PC can be calculated by applying. Then to C again, we apply Raoult's law. Then PC will be P naught C into XC. Now we got P naught C. P naught C 2 10⁴. 2 10⁴ Pascal, and XC is the mole fraction of C in liquid phase. We know that one in the first experiment, 0.3. It's 0.3 unit. It's actually 0.6 10⁴. 0.6 10⁴ Pascal. That's PC. That's a PC. Okay. Then PC 0.6 10⁴ Pascal. Then total pressure, do we know it? Yes. In the first system, total pressure given 2.7 10⁴ Pascal. It's given total pressure directly. Then Pascal cancel, 10 to the power of 4 cancel. It's something like 6 over 27. 6 over 27. Can I simplify this further? 3 times 2, 3 times 9, 2 over 9. 2 over 9, 0 0.1, 0 0.2 something. 2 over 9. Or you can simplify that like 0 0.222 like that. You can do the same thing for what? D. Then XC dash in the first system, right? 2 over 9. We need the value anyway. 2 over 9, it's 0 0.20 mean 2. 18 again 222. That's how we get it. 0 0.22. Then XD dash can be calculated like 1 minus XC dash. Addition is always 1. So it can be like this. In 1 minus 0 0.22, what is it? It's 878. 0 0.78. So the composition of C in the vapor phase in the first experiment is 0.22, 0 0.22. This is now 0 0.78. That's V1, the composition, the symbol they have given, because we use this symbol in the case of diagram. In the case of diagram, we use this symbol. So you can do the same thing by considering the experiment 2. This is by considering experiment 1. Then we go to experiment 2. Do the same thing. Right? Better to write these things because they say then better to write it. To C, we apply again Dalton's law of partial pressure. Then PC will be XC dash in PT, that is experiment 2. But to see again, we can apply Raoult's law, same thing we do. PC equals, we don't need to write that equation directly, you can substitute it now. In second experiment also, P naught C is 10 to the power of 4, 2 10 to the power of 4, why? Same temperature, constant. And XC is different in second experiment, XC 0.6, 0.6. So what is that? It's 1.2 10 to the power of 4 Pascal. 1.2 10 to the power of 4 Pascal. So XC dash will be now 1.2 10 to the power of 4 Pascal divided by total pressure. Total pressure in the second system 2.4. 2.4 10 to the power of 4 Pascal. So what is XC dash? XC dash equals now Pascal cancelled. 10 to the power of 4 cancel. 1.2 over 2.4, it's half, 0.5. XC dash 0.5. If XC dash 0.5, you know XD dash will be 1 minus XC dash, it's a 1 minus 0.5. So that will be again 0.5. You know the question from heterogeneous phase equilibrium, I mean Raoult's, very, very simple. I mean, we can save our time. Quickly, we can do these things. Yeah. Here, XC dash 0.5. Here also XC dash, XD dash 0.5. What is this composition? It's V2. Second experiment, V2 composition. Simply Raoult's law and Dalton's law of partial pressure. That's what I applied. What is next part of this question? I got the answer for first part, second part, third part, fourth part, then fifth one. Diagram. Show the composition of liquid and vapor phases. L1, L2, V1, V2, and relevant pressures in the above two experiments on a pressure composition phase diagram drawn at constant temperature. Now we need pressure composition phase diagram for this. So I have all the information we got here. Then I erase all this part to draw the diagram, the graph. Vapor pressure composition phase diagram. Okay, a few minutes ago, about 1 hour ago, I explained that graph, vapor pressure composition phase diagram. I'm going to draw that one now. Once you ask to draw it, then you have to label all the axes. This is composition. This should be vapor pressure in Pascal now. This is again vapor pressure in Pascal. Everything should be labeled. This is XC and XD. XC and XD here. I take XC this side 0, this side 1. Then XD will be 1 here and 0. But sometime you can, not sometimes, some of you take XD1 here, 0 here, and XC 0 here and 1 here. That is again correct. You are free to take XC0 here or XC1, doesn't matter. Then, but there should be then appropriate changes. XC1, 0 here. XC1 means that is where we get P naught C. What is P naught C? P naught C 210 to the power of 4 Pascal. P naught C, I mark it here, 210 to the power of 4 Pascal. So what is it? It's P naught C. The value and the symbol. P naught C. Then XB D equals 1 P naught D. P naught D 310 to the power of 4 Pascal. 1, 2, then 3. 3 here. This is 310 to the power of 4 Pascal. Actually, no need to put Pascal. It's marked here. 310 to the power of 4. What is it? P naught D. P naught D. Then the total vapor pressure should be then represented. Total vapor pressure. So that total vapor pressure is given by this straight line. That straight line is given. Total vapor pressure. I go to the first system, total vapor pressure 2.7. In that case, mole fraction of C in liquid phase 0.3, 0.7. I told you this line represent the composition in liquid phase. Composition in liquid phase. XC 0.3. Let's see XC here, somewhere here 0.5. Then 1, 2, 3, 4, 1, 0.1, 2, 3, 4, 5, like this. 0.6, 7, 0.8, 0.9, and 1. These are the marks we have. Then 0.3, L1 is 0.3, 0.7. XC 0.1, 0.3 is this. And this is 0.7. L1 is the composition of these things in liquid phase. Composition of component in liquid phase is given by this line. Or total vapor pressure for a given liquid mixture is given by that line. So when you come up, it's this one. So this is where you get what? L1. That point is L1. That point is L1. And what's the pressure? You can mark pressure on this axis or this axis. Doesn't matter. I mark it here. What's the total pressure at that time? At that time, total pressure 2.7 10 to the power of 4. 2.7 10 to the power of 4. That's the total pressure when composition is L1. Next one. Okay, L1, okay. Mole fraction of these, that's okay. V1 should be completed now. V1. But you know, when you consider V1, V1 means the mole fraction of C in vapor phase 0.22. At that pressure, it's 0.22 mean it should be before 0.3. That means this side. So when you get 0.23 somewhere here and this pressure, now you can see it should be definitely below this line. Below this line. I told you composition of vapor phase is given by that line. Then I told you vapor phase composition is given by this line, sum of this line. Okay, actually this line should be very close to this. It's not straight line, it's a curve. Some straight line, it's a curve like this. I hope you got the point. Below line should give them vapor phase. Then V1, where do you place V1 now? It's somewhere around 0.2 to XC 0.22 mean this is 0.1, 0.2, then 0.22 is somewhere here. Shall I take a different color for this? 0.22 should be this place. This is 0.22. This one should be 0.78. Right? So when you take it like this, vapor composition given by this line, not this line. The thing is that when you draw it, you have to be careful. It can't be 0.22 according to my graph. Actually, it should be, you can't change the pressure, total pressure. Then total pressure, this keeping total pressure here, you come here. This is where you get that point. Below that, actually, this is where you get V1. If you come down actually here, that should be end with 0.22. If my graph is correct, if I draw it correctly, this below this point should be 0.22 and 78. You got that point. But according to this one, I don't get it. I get 0.12. It should be 0.22. That is L1, this is P1. It is experiment 2. Then you have to do same thing for experiment 1. You have to do same thing for experiment 2. In experiment 2, P0, C, P0, that's not same value. Those are not different. The question is XC, point C. XC means liquid phase composition. It's 0.6. 0.6 mean this is 5 and 6. This one. This is where now you get it comes up to this line. The above line gives the composition of liquid phase. This is L2. That is where you get L2. At this composition, the total pressure 2.4 10 to the power of 4. 2.4 10 to the power of 4. This is 2.4 10 to the power of 4 point. That's the total vapor pressure for this liquid composition. What is that? It's 0.6. 0.6, 0.4. Right. So I hope you got this point. At this one, this is the total pressure. At this total pressure, mole fraction of XC dash should be 0.5. Then how to get mole fraction at this particular pressure? Then we take it like this. Without changing the total pressure, we come here, and this is where you get then vapor composition. That is V2. If your graph is correct, then it should be exactly on this point. 5.5 is here, right? But in my graph, that means the line should be very close to this straight line. The curved line should be very close to straight line. Then only we can have these things clear. Okay, then we have represented everything, complete information on the diagram. You can see label XC, XD, and 0.1 and 0.0 like that. P0 values. Then variation of total vapor pressure. Then liquid composition in experiment 1, liquid composition in experiment 2, vapor composition in experiment 1, vapor composition in experiment 2. Everything we represented, right? I hope you understood this part clearly. How to draw the vapor pressure composition diagram or vapor pressure composition phase diagram, then how to represent composition of components in liquid phase and the vapor phase with the total pressure of the system. So we have another graph quite similar to this, but the opposite actually. It's about not pressure composition. It's about boiling point and composition, temperature and composition. Because we have relationship between that pressure and boiling point. When this pressure, total pressure, is equal to atmospheric pressure, that will be boiling point. If the atmospheric pressure 1 atm, then it's a normal boiling point. We discussed that relationship also, right? But I think now you need a break. It's nearly 3 hours. Yes. Now we take a break about 20-minute break. After break, let's see what we'll do. We continue this, so then discuss that MCQ part or discuss some question from industrial chemistry. Let's see what we'll do. Right now, first we have the break.